of here with the knowledge that the Standard Model is a high precision, extraordinarily successful theory, which cannot have a problem by definition. How can a theory that is perfectly describing all the phenomena have a problem? So when people tell you it has a problem, don't listen to them. It cannot have a problem. There were people who were saying that Einstein's theory of relativity had problems, people that fought it. That's the last thing you should attack. Why? Because it's very successful. Don't attack theories that work. We like, you know the reason that we like QED? It's not just its beauty or simplicity. It agrees with experiment to 10 decimal places. Standard Model is getting there slowly. Hopefully it will fail. You and I can't wait that it fails, because once it fails, we'll know where to go beyond. Well, one door it opened for us. They proudly predicted neutrino to be massless. This is very important. I tell you, in the 70s, when I was claiming the neutrino has a mass, and people around me were worried, I'll tell you why. I was told I was wasting my time by the fathers of the Standard Model and many people around them, because neutrino was massless. Everybody knew. So this is the door that we should study. When you want to do physics in the future, look where the old physics failed. Forget semantics. Okay, that's the message that I want you to get out of the course. Besides manipulating formulas and predicting things that will become data. Okay, this is very important to me. So, what did I teach you the other day? I kind of started to prove Goldstone theorem in a poor man's way. Right? I give you an example, it agrees, but I think these examples are very useful because slowly you get a feel how it works and not just a generic proof. So what did we do last time? We did SU2. We did one example, so we are still with Nambu-Goldstone picture. Scenario, idea, mechanism of spontaneous symmetry breaking, right? The idea of global symmetries that are respected by your Hamiltonian or Lagrangian, but the ground state refuses to accept them. So we did SU2 with a doublet, which transforms as U5, where U is the SU2 by definition. I could write 2 times 2, you know, every time, matrix, just to make it clear. And determinant 2 is 1. We wrote our usual potential, being trivial as it is, right? And what we found out, that the vacuum manifold, I'll just summarize for us, was S3. Why? What we've learned, you know, once I've learned that phi 0 is non-zero of the vacuum manifold, I choose it in the direction that I like. I'll be doing that a lot. Sometimes I'll show you explicitly that it doesn't matter how I choose it. The other times I'll just ask you to believe it. If you doubt it, choose another one and verify. It has to be independent of my choice because there is a symmetry. And I chose phi 0 to be this. By the way, it wasn't really important. You see immediately, whatever the choice is, the TA phi 0 is not 0. TA are Pauli matrices. So that means that I have 3 broken generators, we say, in our language, 3 broken generators. We should imply, if Goldstone is right, 3 massless Goldstone, Nambu-Goldstone bosons. So there are 3 G's, so that Mg is 0. It's not Ng, we'll call it G, a Nambu-Goldstone boson. Let's take now another example. I will need this blackboard. Let's try that is maybe a little more illustrative. Because this is a sort of rare situation when all the symmetry is broken. Okay, please.
How do we distinguish between these 3 Goldstone bosons? What's the difference between?
Well, it's a very good question because, sure, it's a nice question. I'm glad you're asking. And it sort of goes with the next thing that I want to do, because I said this is a rare situation when all the symmetry is broken. So I don't have a classifying symmetry to think about. So I can't really distinguish between Goldstone bosons, right? They possess the thing that they belong to all that is broken. But what we are going to be studying in the standard model, and especially beyond the standard model, imagine now that you go to the, well, you know what happens in the standard model, so let's say it immediately. What will happen in the standard model? The theory is SU2 cross U1, right? We said it had to be SU2 cross U1. You know already what I have to do, right? It can't be SU2. And it will be broken down to U1. And this U1 is electromagnetic. So I will be able to classify these Goldstone bosons by their charges, for example, and they will be distinguished by that. So I need something to remain that I can talk about. And suppose that I want to do what we call grand unification. This is unification of electroweak. Now I want to be grand, right? So what does it mean grand? Then I have some big gauge group that I break down to the standard model. It's a symmetry up there. For example, this symmetry is only valid that the energy is above the scale of breaking. The scale of breaking is the mass of the W and Z, right? When I'm at very low energies, there is only this symmetry. So this will be valid at even higher energies, okay? And the standard model also has SU3 color, as you know. So now you know it's even easier to classify. My so-called Goldstone bosons would be, you know, I can tell you, are they colorful particles? Are they colorless? Do they have weak interactions? Do they have electromagnetic interactions? You see, this is what we need, and fortunately in physical example. So something remains. So this example was just a group exercise. This is not how the world looks like. Or maybe it is, if you learn that even U1 is broken. Somehow you tell me one day the photon has a mass. What can I do? I'll break U1. I didn't want to break SU2. It's a beautiful symmetry, but you tell me the W boson has a mass. Well, not me. You tell Weinberg, he says, okay, I'll break it. What's the big deal? I've learned spontaneous symmetry breaking. I can break anything. Unfortunately. We may even be puzzled with their any symmetries a while, you know, this violence. But we don't know. There is good indication that some of them do, you know, we believe that SU3 color, I'll have to talk about it. It's actually exact symmetry. You know, exact symmetries are something very strange. Nothing is perfect in this world, right? A perfect soccer ball, you know, if you have a microscope, won't be so perfect, okay? The symmetries are there. We always felt to be approximate. We should be surprised about perfect symmetry. And some people don't like them. Some people say, no, I'm going to break color. The other girl or guy says, I'm going to even break Lorentz symmetry. I don't like anything, you know, nothing is sacred in this world. But this is standard model, so I won't do that much break. So now I want to do examples when something remains. So I'm going to take SO3. SO3 is really equal to me. I'm not very mathematically rigorous here. I think of an algebra, but when I speak of SO3, I mean I have a vector representation, not a spinor representation, right? So it's SU2 with a vector. There is another name we use for a vector. Vector means it has 3 components, which there is a particular representation that has 3 components. It's called an adjoint representation. It's the representation, for example, of the gauge bosons. If you've seen, notice that when I wrote the gauge bosons in the Young-Mills case, I didn't write it as a vector, right? I used something very strange. You remember how A transformed?
Plus 1 over G.
So, you know, we often do this. You can do this. This is very convenient. we write like this. It's a nice bookkeeping, right? Instead of working with components, we take the matrix of these fields in the basis of my traceless Hermitian generators of the group. I can do it for any group, right? What we wrote there, it wasn't SU2. And then we found out that A mu transforms into u, or u to the minus 1. It's where you put it, it's irrelevant, okay? It's a definition of u. I can call u dagger, or vice versa. A mu. If it's an SU transformation, I can just write like a mu dagger, u to the minus 1 u dagger. And it, of course, has a gauge dependence there. Gauge dependence because I'm talking about something which has to do with local transformations. But the global part is here. So this is called an adjoint representation of a group. Adjoint means that it's adjoint to a generator. To every generator associated field, we call it an adjoint. And gauge bosons are always an adjoint representation. That's how it works, right? This is what Young and Mills is, this miraculously beautiful work. It's a generalization of QED, which there was one generator, okay? The thing that sort of, maybe the first great revolution in the theoretical mathematical formulation, 1954. The golden eras of the 50s. There are two golden eras in the 50s, and 60s miracles will happen, okay, I remind you. So when I say that I have a vector, I can write it like this. I can write phi in this form, like a triplet. I could write phi as a vector, that's what I mean, and call it phi I, and then I go in some basis of unit vectors, right? I don't know how to call them. There are many ways we can write a vector. When we were little, we were always writing like this. Then we grew up and learned that maybe even more convenient sometimes to just put it in a column. Okay, if I put it in the column, phi transforms as O phi, where O transpose O is 1. And determinant O is 1. And then I can write O as e to the I, that I, ti. Now ti, I know immediately something interesting about ti. They are of course Hermitian, as they're very messy too, but they also have to be imaginary because O is real. So I have generators ti dagger equal ti, where ti star is minus ti. They're imaginary. And they had the famous form that we cited when remember when I studied a spin 1, when I was talking about the polarization the other day of a Proctor field. For example, T3 would look like this. And so on and so forth, right? Ti, jk, is minus I epsilon I jk. You know, I can generalize this to any SUN group. I would put, instead of epsilon, I would put Fi jk. This is always a representation. It's another name that is associated, a joint, a good way to call it a joint, right? It's a joint to the generators themselves, okay? To the structure constants of this. You're all familiar with this. Let's try to think about this in both. Well, I need you to be really comfortable with both of these, adjoint and the vector representation. You should be able quickly to go from one to another. You see, in this particular way, when I do it adjoint, I'm using the same U as if I have a spinor representation. this u here has nothing to do with this generator. Here u is e to the I, of course, same I, but the I are not these, they are Pauli matrices. Obviously, this is all done in the basis of the group. These are Pauli matrices. Okay? This is very important that you understand. I'm writing u dagger. This is my SU2. And adjoint of SU2 is equivalent to the vector of the SO3. We'll see. You're all familiar with this? So notice almost, I don't feel like writing even this, we could make a guess. So let's make a guess and then let's write. We have to do the both things, yeah. These are trivial calculations, but it's not easy to know what will happen in advance. Most of the time, you and I learn by doing a calculation and then understand what is going on. People say that around, I had friends who were at Caltech in the time of the peak of Feynman, and they said even Feynman had, lengthy notes of calculation. Because when you read Feynman or listen to him, it seems that it's all here, right? That he doesn't have to compute anything, you would feel, right? The understanding is out of this world. But sometimes calculations will be very long. Try to think before the calculation what you will, what you may get. In particular, when we have situations with symmetries, symmetry arguments are very useful, as you know. For example, if I have a spherical symmetry and I get a result that doesn't respect it, then I know I was wrong. I can think about I can guess a result very often. Not always. I cannot overemphasize this. I'll come back to this when I do more less trivial example. I have a personal example to talk about. So what do you think happens here? Now, what will the symmetry be broken to? I said it the other day, but you can see here. Look at this generator. This generator, I say, if this generator acts on this, whatever is here, it gives me 0. I don't even care what is here. So what is the smarty thing is to rotate my vacuum in that direction. And I see immediately one generator won't be broken. So by doing no work, and this is not surprising, I'm saying when I choose the vector in the z direction, something must remain, and these are the rotations around the z-axis. So I would guess here, without doing any work, that this symmetry, or I should have said here, okay, let's keep this. SU2 we said like this, gets broken by the doublet, let's call it doublet, vacuum expectation value. Let's keep this on the blackboard. And I expect that SO3 gets broken by triplet non-vanishing vacuum expectation value into SO2. Which we also write as U1. Right? Because that's what it is. Either I write something as real and imaginary coordinate. It's like writing a complex number. I expect this without doing any calculation. So let's be a little more careful. So let's do this here. My Lagrangian would be 1/2 d mu. Sorry, I'm already running it. I want to do gauge theory. I want us to go there. Phi transpose d mu phi. Right? O transpose is 1 minus V of phi. Well, this is equal now to phi, triplet. That's what I mean by T, a triplet. Maybe I should have actually used T as a notation, but forget it now. And this is lambda over 4, phi transpose phi, minus V square, everything square. It's becoming a better thing, right? I hate this part when I'm writing always one and the same thing. So what is my vacuum manifold? Set of all points phi 0, so that phi 0 transpose, phi 0 constant. I want to minimize both. I want to minimize everything, right? Hamiltonian will have derivatives. So this is v squared. And this is S2. I look at this and now I decide. I call this phi 0 Goran. Check it. I can always choose it like this. This is trivial. This you always knew. For a doublet, maybe you didn't know that you can rotate it, but it's trivial to show that you can rotate the doublet too. This, of course, you know. That's a definition of the z-axis. Okay, I'm defining a z-axis. So obviously, T12 acting on phi 0 do not annihilate. They break it because T1, for example, will be how? What will be T1? In the direction to S3, right? And T2, direction 1, 3, right? It's written here. And T3, acting on a phi 0, is 0. Therefore, now I see immediately that SO3 got broken. So I expect two Nambu Goldstone boson. This is how, as a student, this is how we would do without thinking deeply. We would take this, what we call theory normalizable, and we would write phi 1. No, we wouldn't write this. We would write G1, G2, V plus H plus IG3. No. No, this is not smart. This is better. There are 3 fields, right? Not 4. Well, I should have left for you to comment. Okay. I have 3 fields, phi 1, phi 2, and phi 3 that I call them here. And I'm saying that the third field lives around the vacuum. This is going to be what? We can guess. This is this funny, what we call Higgs field. And we can almost write immediately what the mass will be and so on. But let's check it. So what do I have to do? The V of phi then is lambda over 4. Phi transpose force is G1 squared plus G2 squared plus V plus H squared minus V squared, everything squared. Well, this is lambda over 4, 2VH plus H squared plus G1 squared plus G2 squared, everything squared. And I see the situation I've always seen. This guy gets a mass. These two guys don't get a mass. There is no quadratic term in G. And I see immediately that mh squared is 2 lambda v squared. I can't overemphasize that, and this is what we expected. And it has to happen every time because the only source here of mass is the vacuum expectation value. So the mass must be proportional. The way I normalize there is a factor of 2. It has to be proportional to v squared. And how does it get a mass? By coupling to this vacuum. And the only coupling is lambda, so it had to be this.
And the V beyond the dimension of the parameter.
That's right. And GI is 0. I can see that immediately. I could have also said, why don't I write phi, what I call phi unitary, as e to the gi over v ti acting on 0, 0, v plus h. I can write in the usual form, or I can write as a phase. Remember, I can write as a phase because TIs are imaginary. This is real. This is fair enough. If I expand it, it's going to be, I'll get trivially the other thing, okay? It seems, you know, you may be confused because there are 3 generators. Say, how did I, what is this? I got 3 GIs? And 1H, I got 4 fields all of a sudden? Well, it's misleading. There is no G3 because T3 acting on 0, 0, V plus H is 0. So there are only 2 of them. And of course, they disappear from the potential. This is nicer. I'm in the basis in which the potential now is lambda over 4, just V plus H squared minus V squared, everything squared. There are no G's. Phi transpose 5 gets rid of G's. Do you see that? Why don't we do it? Phi unitary transpose. Phi unitary is 0, 0, V plus H. I studied too far. Phi unitary transpose. Phi unitary is 0, 0, V plus H. E to the minus, no, plus GI TI transpose. E to the I, GI, TI, 0, 0, V plus H. Correct?
Basically, you look at that TIs are antisymmetric.
They are antisymmetric, precisely. So I will get this from here. It's always, it's a smart man, you know. This was a poor man's way of doing it, you know, or a dummy's way of doing it. And you are tempted to go in this, in order to understand what it is, this sort of unitary picture. It's very convenient because you see immediately what is going on. You don't have to compute anything. Just get rid of these guys. Of course, they'll go to the kinetic energy, that's okay, but they're going to be massless. You see, this is sort of a way of proving it. Just write like this, and what will come out are the broken generators. The only guys that survive here are the generators which are broken. In the unitary representation, Goldstone theorem is basically obvious. Right? I always do that. The generators which are unbroken, there are no fields associated with them because they give 0. And the ones that go with the broken generator disappear from the potential, therefore they are massless. The only place where they get the mass is the potential itself. Right? You see, at this point, you and I should accept it if you are not very rigorous. No, maybe for you this is not good enough, so I'm not sure. I'm happy with this for the moment. I may change my mind and prove it.
That's the rigorous way to prove it.
Well, it's better not to say it in words. If I decide, I'll do it, okay? Try to think about that. I don't want to do it so lightly. Let me think whether, to me this is rigorous enough, by the way. You can see the way I do physics, right? My group theory is here. It's not here. I'm sort of complementary to Narayan, it's all here to him, it's nothing here. But he's good with his fingers also, but he doesn't use his fingers, he does a fancy math. What I do is always Pauli matrices, it's embarrassing, I'm sorry. Because I'll always do the adjoint representation. Adjoint representation is Pauli matrices, but you can tell me, but you've been working, you can see I've been working on SU5, SU10. Well, you can make SU5 with Pauli matrices, as we did in SU3. all you need to know is SU2. Even Lorentz group is basically SU2. Well, think about that in the Euclidean space. Well, time, unfortunately or fortunately, is a little different. It's this bloody error. You don't care, you know, I care more than you guys about the error of time. But in Euclidean space, it's SU2 cross SU2, right? Because in the Euclidean space, boosts are rotations. In our place, it's just a minor difference, okay? You don't get, there's an extra factor y. But anything that you can still use Pauli matrices up to this factor y, right? When you do the boost. So I would really want you to walk out of here having SU2, you know, maybe you have it already, completely under control, okay? That you can work out any group without fancy, you know, not knowing Dinkin or any fancy stuff like that, okay? That if you do, so much the better. But not at the expense of this basic. Notice that there was just one invariant here. It is trivial. You've been used that there is just one invariant. The only thing that you can write is the vector square. That's the only invariant that you can write. And it's not surprising for a group of rank 1 to have only one invariant, right? There is only one generator that you can diagonalize. Now suppose that I use the adjoint representation. Let's just try to say a few words. Well, I don't know. Let me see if there are questions here. I don't know if I want to say anything. In this example, we are sort of now slowly nailing it down. We can pause for a minute. These two examples are almost enough to understand everything. What they lack, however, is the subtlety of group theory. So I'll give you a sort of hard homework, which there is a subtlety. SU3 group with a joint representation is a beautiful subtlety here, although it's a simple group. It can be worked out. The subtlety is beautiful. It's not so hard to work it out. I often suggest for extra credit to break SU5. It's sort of fun. If you do it, which I would encourage you strongly, you actually learn in that exercise the essence of grand unification. The rest would come easily then to you. But so you know, in SU2 it's okay to work with a vector. But imagine now that you have to do it in SU3. Now it has 8 components, right? It's a mess. So it's not epsilon, it's F. You don't know structure constants of SU3, I can bet you. You could, I could lose, you see. It's one of those bets, the risk, there could be someone that knows that. Maybe one of you knows that. So obviously this is the way to work, you agree? Because you always know the original representation. It's trivial. You know the Gell-Mann matrices. What a funny thing to call Gell-Mann, right? Because physicists didn't learn. It's amazing how much you have to learn today. Think of that, formally speaking. Don't mean that they were dummies. You know, as I like to say, they were not completely stupid. They had to learn a lot of other things. You know, there is always. But in mathematics, it's funny that you call them Pauli Gell-Mann matrices. You know, these guys didn't study any group theory, obviously. So let's do it. Let's do it with the adjoint. So with the adjoint, I can come back to this. I need a blackboard. So I could write like this. I could write adjoint is phi I to have the same notation ti. I could still call it phi, but I called it before. Now this is now a matrix, right? I'm expanding it where ti is sigma I over 2. I can write as a vector, I can put in a column, I can also put these 3 guys. These are the same 3 guys. I can organize like this. Right, so how would it look like? It would be phi 3 minus phi 3, phi 1 minus I phi 2, and phi 1 plus I phi 2. And there is a half. You don't even have to put a half, it's up to you. Write that, okay. Typically we just take the generic. You would write the potential now. Let me just write the potential. How would it look like? Lambda over 4. What is the invariant here? A transforms into UA, U dagger. Just like the gauge bosons. What's the invariant?
Trace of.
How does A squared transform? U dagger. So I have a quadratic. Also transforms like a joint. And the trace of A squared is invariant. You see why I'm taking, by the way, you see what I've done. I'm taking trace A to be 0 by expanding this. Because just if you look here, trace of A is invariant. I'm always looking, I'm after irreducible representations. The trace of A is what we call a singlet. Forget about that. I want to have the minimal set of fields that transforms in a certain manner. So when I say the adjoint, it's done here. This is why I expanded into this basis of traceless 1, okay. Instead of having 4 components, as naively when you look here, it will have 4 components, it has 3 because trace is invariant. Trace of A goes into trace of A. So I can discard it. So I will have here trace A squared as invariant. Of course now it's normalized differently, so what am I going to get for the trace A squared? What is trace square in my notation? Trace A squared is phi I, phi j, trace Ti, Tj. What is trace Ti, Tj? Help me. No, it can't be 2. They were normalized. It looks too big to me.
Okay.
It's probably a half. Yeah, okay, sorry, because you're right. You thought of Pauli maybe. So it's 1/2 phi I, phi I. So I get back the same. This was my invariant. This is 1/2 what I call phi transpose. So there is some normalization difference, right? So it would be smarter to write V squared over 2 to get the same vacuum manifold in the same, not to get the same vacuum manifold, in the same notation as before, I'm sorry. Square. Well, you could tell me, how does A cube transform? So you could ask me, here, for example, you could ask me, this is a typical question, when I tell you for a doublet there is just one invariant. There are actually many invariants I can write, but I don't write them. Trace A I don't write because this doesn't exist. This is a traceless matrix. But this, you can ask me why I'm not writing this term, for example. This is a sort of, of course, understanding the, but you answer to me, why I'm not writing this term? Assuming I'm not completely stupid, but I'm not in that category. I can't say that I'm not completely stupid. I remember my younger collaborator asked me, can I say I'm not completely stupid? I said, how can you imagine? I talked about Einstein and Newton and so on, you won't be, I wish I could say, in that category we are all completely stupid, right? I mean, that's what to do. At some level, maybe, you know, but not at that level.
You mean like writing this potential plus a 10 base trace of A?
I have to write all the terms up to quartic order. That's the rule. When I do the doublet, I cheated, you know, there were a lot of terms I could have written, but I didn't write them. I knew that there was just one invariant. By the way, there are different ways of doing it. You can be smart, or you can just, you don't have to be smart. Then you have to compute. Either you tell me that you know why I'm writing just one term, so if you give me a proper rigorous mathematical answer, you don't have to do it. Otherwise, you have to show to me why this is zero. This is zero.
This is okay.
Well, you know it. The trace of sigma I, sigma j, sigma k is zero. This is what I mean that you know group theory. They should be in your fingers. Why is it zero? Yeah, well, because of the commutation relations and variables. Also because sigma I, sigma j is delta ij after a factor plus I, epsilon ij, k, and so on. And they are traceless themselves, so when I multiply 3 times, either I have epsilon or I don't want to do it. Because this is trivial. What you can do, you can say the following. You can say the following. I can always choose a vector in one direction. For example, when I want to prove that there is one invariant in the case of a doublet, I'll take doublet in one direction, and I see that there is only one invariant, the others goes to 0. So that means there will be one invariance, whatever basis I use. Number of invariants cannot depend on the basis. I can always rotate a vector. That's why there is only one invariant, which is vector square. Because vector really has one component, not 3. Well, it has 3, but I can go into the basis where it's along the z-axis, okay. I check there, then I say, okay. And what corresponds to, tell me what corresponds to the choice of a direction of a vector? You see, notice that actually adjoint representations are Hermitian by definition. Now let me do what I didn't write immediately, and I didn't want to do it on purpose. These are Hermitian matrices, which are traceless, okay. Hermitian matrix, which is traceless. I take it Hermitian because Hermitian remains Hermitian under this transformation. I'm taking irreducible representation that transforms the same way, okay, whenever you have that. That's why in Lorentz group, it's a left-handed spinner, which is an irreducible representation. That by itself transforms. I never have to introduce the right-handed one. So adjoint in general, when I say it transforms like this, all I know that there is some matrix that transforms in this manner. Hermitian part transforms the same way, so I said I'm going to take that part. Trace is 0, so I'm going to subtract it. Okay. So this is the definition of the adjoint. Plus this. And what can we do with the adjoint representations? With Hermitian matrices. Vectors we rotate in one direction, and Hermitian matrices we can always diagonalize. In the diagonals you will see immediately there is just one invariant. There is basically one component in that basis. But you are allowed to do that because you are allowed to choose the basis any which way you want. Okay. So remember this. So for example, I'm going to say in my vacuum manifold, it's again S2. It's the same. It's the same invariant. Okay, I have nothing to say. But I'm going to say that I'm going to choose A3 to be T3 times V, or V over 2 or something. Tell me, what is it? V over, I don't know, over square root of 2, I think, in my basis. Let me think. I'm not sure. I need your help. So trace A square. So I've written A as A0 times V, right? Sorry, no. A0 times T3. No. No, what? I'm writing A0. This is when you don't want to look at your notes. You see? You pay a price. I'm saying I'm going to take it to be T3 times, how will I put X. And let me do it as a dummy. Trace A0 square is X square. What is a trace of T3 square? It's a half. And it has to be V square over 2 in order to minimize the potential in that thing. So X is V. So why did I want to put the square root of 2? I see, I had doubts. Sometimes you should trust the first thing you write. Most of the time you'll be wrong, but anyway. Okay, agree? I can always do that. I can take my adjoint in these pages. And I can see immediately that one generator will be unbroken. How can I see that immediately, what I mean? Do you see it? If you don't see it, I'll do it. Well, before I do it, I could ask you the following question. And this is what I mean, that the generation after generation comes to me, they tell me that they know group theory, they've taken a group theory course, they do it before coming here and they do it here. And I always find that they really don't know SU2 to make me happy, okay? But maybe you do. So tell me, for the adjoint representation, what are the form of the generator? This means knowing adjoint representation. Osman knows it.
Epsilon A.
No. There was a vector. No. This is equivalent to a vector, but this is not a vector, this is a matrix. I'm not asking you what are the generators for phi. I'm asking you what are the generators. You see, I put a hat here because I'm generalizing it. For this particular crazy matrix, you can ask me why the hell I knew what the vector was. You know, who was this moron? Why did Young and Mills do this stupid thing, right? Well, C and Young was not completely. Well, he's still. Jesus, I wanted to say he was not. By the way, he's 98 in a great shape. I haven't seen him this time when I was in China. I think he's in Beijing. I saw him 10 years ago in Gelman Fest 1980. He was 88. He was amazing to see. He gave he walked as a young man and gave a talk with authority, and I love to see that when people still work at 98. You see, what do I mean by a generator? Remember, for example, doublet transforms is e to the I. Everybody transforms like this, sorry. But doublet and TA is Pauli. So what I mean by this, 1 plus I can just look at the reading term, D, and I know I define it to be sigma A over 2. So what I mean is, how does my A transform? My A, my matrix A. Well, I can just make it. Well, I wrote it like this. I don't have to do it. It's a matrix A transforms into UA U dagger. U is e to the I, theta I, sigma I over 2. So this will transform into 1 plus I, Ti hat, theta I times A. Formally written. That's what I mean, the leading term, right? Plus I volume. Well, we can do it, but I was hoping you will remember. So you didn't do the adjoint in the group theory course. You did. Well, let's do it. So this will be 1 plus I, Ti, sigma I over 2. Well, let me call it, say, theta j, sigma j over 2, A. 1 minus I theta k sigma k over 2. I'm looking at the leading order to recognize the generator. All you need to see the first term. That will tell you how the generator looks like, right? They will sum up correctly. And this is what? This is A plus I Tj sigma j over 2 commutator with A. So Ti acting on A is TIA. In the picture that we use, the joint picture, what I mean by knowing SU2, all you need to know is Pauli matrices. There is no other representation. We'll do everything through Pauli matrices. All we have to remember how the thing transforms. If I take a symmetric representation, then maybe it will not be a commutator, some other thing. But I don't want you to learn anything else but Pauli matrices. So when I tell you that you have to know group theory, all you have to know is Pauli matrices. The rest will come for free. But that you have to be able to reproduce or remember. Okay, a joint is very particular, it's a commutator. I make it dramatic sort of, so I want you to remember, okay? I don't want this goes en passant and the next time when someone else teaches that I'll tell you when I'm going through this course, what are the things that you will have to remember? There may be 5 things. I know that most of the things you'll forget and you'll have to, remind yourself. You'll be doing PhD and again you'll be taught and taught in another way. And that's why it's good to repeat things. So that means once I put it in this direction, I can see immediately which direction is annihilating a vacuum. Not breaking, it's T3 itself, because T3 commutes with T3. It's an interesting thing what you can say about the adjoint representation. Suppose I ask you the following. I suppose I took SU5 for some reason, and I took an adjoint of SU5. How many generators in SU5?
24.
24. I don't want to study symmetry breaking. I don't even know which direction the web will go. That's a non-trivial study. That could be a complicated homework or a take or an exam. Oh, by the way, we'll talk about that. Normally, I give you a choice. You can have an exam in class or take home.
Take home.
Everybody chooses take home. I'm glad you say that. I love that. I'm an American product, and we have mostly take homes. And that's one of the reasons I really loved doing my PhD. Okay, I never had to study almost. If you like solving problems, then there is nothing to study. Okay, really, in the sense of learn. I think one of the reasons I do physics, honestly, I didn't like to study very much. And it was a great discovery to me that you didn't have to study math and physics. You could reproduce things. So tell me what generators, you can tell me immediately some generators will not be broken. You could deduce something interesting immediately. Well, it's not obvious, so I'll try to give hints. When we do the Lie algebras, the group, the first thing we do what Cartan did. The very important part of a group is a Cartan subalgebra, right? What is a Cartan subalgebra? It's the collection of all the generators TA, so the TA TB is 0. How many such generators in SU5?
4.
4. In general, there will be 5, but they are traceless. There are 5 diagonalized 5 times 5 matrices, but of course they are traceless, so they are 4 independent. Okay. So Cartan algebra is 4. Can I break Cartan algebra within a joint without doing any calculation? So I don't know what the vacuum manifold is. I will have some A0. So what am I going to do? For a vector, I took a direction, right? Direction meant that I chose the z-axis for a vector. For SU2 adjoint, what did I do? I diagonalized it. I can always diagonalize the Hermitian matrix. Therefore, A0 is diagonal. No matter what you do, this is the most general value you can get. This is when I tell you before doing a calculation, it's always good to do these things. You know, you think I want to know what I will, what I should get. So it's diagonal. Diagonal commutes with all the diagonal matrices. So you cannot. We say that another fancy way of saying it: a joint cannot break the rank. Cartan will always survive. And it's kind of nice. You see why a joints can be nice. The rank of SU5, you knew, is 4. Rank is the number of cartans. The guy is inside cartan, so it's 4. What's the rank of the standard model? Kevin is counting. It's only your fingers, I told you. You know, you don't need it here, you need it in your fingers. I like that. It's 4. So see, you know, oh, imagine you are Georgia and Glacial. Imagine you'll be speaking in the afternoon, and you are a group theory wizard. Howard Georgia is a group theory wizard. Probably Glacial also to some degree, but Georgia, when you know him, it's sort of amazing. Once I was working, I remember on SO10 for months with Mohapatra, and we got badly beaten by Georgia and his collaborator. Couldn't publish a paper because I could see the difference, you know. I think he also has it here, you know, I'm basically mostly in my finger. And, well, he claims, I can believe him, that he did in the same night SO10 and SU5. It was a white night, obviously, you know, it's an epiphany when you realize that some magical thing can happen, that you can unify all the interaction imagine in a single group. These are moments which are rare, even if you're a great physicist. But what was useful, the why they could see immediately has to be a joint. You can ask yourself, how am I going to break SU5 and get standard model? Well, it has to be a joint, because you don't want to break the rank, as Kevin told us. For example, if I take a fundamental representation, we break the rank. Remember when we took the tablet? We broke the rank. You can't preserve the rank with a fundamental representation. You can try other representation. You will see that tendentially you break the rank. With the tablet, for example, we work all of SU2. For example, if I'm trying a group theory on you, okay, so let's do these 6 both. Learning and guessing. Learn, you know, calculate, you know, this is what when I teach here, I struggle a lot. I can't overemphasize the importance of calculation, so I will give you problems that every sign matters. I also want to emphasize not to do too much calculations and to think more. And this fine line to walk, it's very hard. The reason I'm obsessed with that, I had a period when I didn't want to work with my advisor. I was very sort of, I have a one-track mind, and it is very funny because we wrote a paper that became very important, and I still didn't want to work with him, so I was working on my own. And my advisor was a great, great collaborator of mine later on, Rabbi Mohapatra. But he never had time, you know, I was working on my own, so he was busy. So he let me go on for 3 months. One day he calls me in the morning, he saw me in the office, it was 10:30 in the... He says, okay, tell me what you're doing. I've been calculating for 3 months. And I will never forget it, of course. And he stared at what I was doing, and it took him maybe less than 10 minutes to show me that I was calculating 0. It was a very painful moment. 3 months. I walked out, and I walked the whole day on campus. I came back at 4:30, and I asked him, well, you think, am I completely stupid, you know, when you do this kind of thing, really, in a sense, you think I should go home? He actually encouraged me very nicely. He said, I think you are really, really good, you know, it was very... So I tell you about the mistakes that people commit, and he told me a beautiful example. He and Jogesh Pati, a great physicist, you know, father of the Pati Salam walk. The ideas of grand unification started here with Pati and Salam before Georgia and Glacial to unify quarks and leptons, you know, in a great work. And Mohapatra and Pati had a paper on CP violation They were just about to send it out. He even gave a talk in Maryland, where he was. And in the evening, after the talk, before going to give a talk somewhere else, he realized that he could unwind this CP phase. You know, CP violation means that you have a complex phase. But not all phases are phases. Alexei must have told you that Kobayashi Maskawa start with 6 phases and end up with 1. That may happen. You can end up with 0 if you're not careful. You know, for example, with 2 generations, there is no phase, you know. Then he gave me some, there is a beautiful example I'll tell you when we studied the standard model that Weinberg's beautiful paper in 1972. Weinberg did not want to learn 2 things, path integrals, and he couldn't stand that this little Dutch guy, as they call him, that Hoff beat all of them and proved that the spontaneously broken gauge series are normalizable. And it had to do with sort of choosing a gauge, you will see that. So after Hoff shows that it can be done, Weinberg now wants to show that he can also do it in this old-fashioned way of doing things, okay? And it's amazing, he had 2 mistakes in the paper. The first mistake is my boggling. In the Young-Mills equation, he must have been checking for a month. He made a mistake in the first formula that he carried on. And Weinberg is not just a great physicist, he's a master of field theory, as you probably know, right? I mean, just look at his field theory book. So it's reassuring. So, but you see, so it's always good to think, to make this long story short. Think about group theory arguments, whatever. The measurement arguments, whatever you have, before and of course after when you get the result, before you hand in the homework. Homework. You will see a neat subtlety when we do SS3. We do SS3 in adjoint to appreciate the use of the adjoint, preservation of rank, and so on. And then you'll try to sort of see what is going on. I think at this point, I could stop. Now, how would I write that? You know, I wrote, how would I write my A in this basis? So I wrote this at T3 plus V. So in other words, I would write this 1/2 V plus H minus V plus H. You agree? That's the smartest thing I can do. Because H is where I live. It's this perturbation of the ground state. It's the excitation above the ground state. So I always have to know room. And then I call these guys, obviously, G1 minus IG2 with the notation that I've done. And it's a trivial exercise that the trace of A square anyway is the same thing as before. So we'll get 2 Goldstone bosons. This is the way you would do it in the adjoint representation. So remember, whenever you work with adjoint, you will diagonalize it. Of course, if it's a bigger matrix, it may not be enough to diagonalize it. You may have to really minimize, find the minimum, because there may be some global maxima and so on. It's easy in one case. There's just one direction. In SU5, there can be different directions, right? The fact that it's diagonal doesn't tell me in which direction it goes. But the crux is here. Higgs is the guy who lives always around the web. Accompanies the web. And we see it in this basis. I could also write A. This would be A renormalizable. And I could write A unitary as, you know, use my old trick. Where there is U, I just write E to the I, GI, sigma I over 2. I would use A0, so I would write like this. V plus H, 0, 0, minus V plus H, E to the minus I, GI, sigma I over 2. You remember what the trick was? Here, instead of writing in this sort of, which was real and imaginary, for a doublet, we could write this as phase, so I write the Goldstone bosons as phases that accompany the generators. That means I use the center transformation property they have and put them in the phases. It seems that there are 3 of them, but remember one generator sigma 3 commutes with the vacuum. So there are actually only 2 Goldstone bosons. And they drop out immediately. In the trace, there are no Gs. Check it, please. I just said it in words. I think you see it, right? It's trivial. Trace squared, is trivial. A squared transforms the same way. Anyway. I'll never mention vectors anymore. Whatever I do, I'll be talking about the joints. It's a much better language because we can generalize it to whatever group we like to think about. SU3 is already non-trivial, and as you can imagine, SU5 becomes sort of something that requires a careful study. Any questions here? At this point, I feel I've proven the Goldstone theorem in a poor man's way. It's kind of obvious, right? Whenever I can always write in this way for whatever group, think about that. And then what will remain here are the guys that accompany broken generators. And they will definitely be massless. To me, this is good enough. Well, you see why it's not good enough. It's not any group. This is, for example, in SU groups and so on, okay? I'm not saying any groups. You can ask me what happens in an exceptional group. Exceptional group, you don't easily write exceptional group. E6, you know, we don't have a nice, easy vision of E6 of the representation. It's easy to talk about SO and SU. Basically, it reduces to this. Well, physics, of particle physics is all about SU groups. Many people think that maybe there is even SO. SO10 has been studied by a lot of us. I spent a lot of time studying SO10. There were people who claimed, no, you see, because it was interesting. Feza Gersi, who was a great physicist, Turkish physicist at Yale, a great expert of group theory, he says, well, there are infinitely many SU groups. So I don't believe the right group should be exceptional because there are only a few of them. See, there are these interesting feelings, how we go about intuition. I would never subscribe to that. Then standard model should have been an exceptional group, but that's logic, who cares? There are always infinitely many. You know, when I have an idea of Einstein, there are infinitely many Lagrangians I can write with that idea. He just took the minimal one. Nothing wrong with minimality. It worked beautifully before. It's not true that you needed an exceptional thing. So Maxwell did the same. When I write a Maxwell Lagrangian, there's just a simply Lagrangian consistent with the But anyway, I mean, this is a it's sort of interesting because I've been sort of insisting on this. Well, it's not mine. It's everybody really smart said it in the past. Feynman used to say it, and it cannot be overemphasized. It's very simple if he says, make a guess. I don't care what your guess is. Don't debate your guess with me, and I won't debate your guess. Compute if you can. If you can't, forget it. You see, when Einstein writes that thing, he doesn't want to convince you that you have to subscribe to that. That's irrelevant whether you believe in Einstein or not. What he has to do to show you that he can do all kinds of correlations in a structural manner, not by adding anything else. And then you get someone to measure. Right? This is very important. So it's not an issue. You see, this is what Gleshow did. This is what I cannot overemphasize. It's not that, because it's very interesting. I wrote this, you know, I told you that this talk will be about this sort of essay that I wrote, and it catching a lot of attention. There is a very important blog which is called Not Even Wrong, And this guy says, oh, I like Senjanovic talk a lot, except I completely disagree with him about left-eye symmetry. I'm sure it's broken at the fundamental space-time level. Well, he completely missed my point. I don't care whether you subscribe to that or not. I'm not asking you, I'll have to explain to him, and I will. And you also, when you write something in the future, don't try to convince me that you have a new model. Just tell me what you get. If it agrees with the experiment, I'll buy it. Okay. I'm saying this because I have nothing more to say and I'm waiting for a question. You see, if you wait long enough, you get a question.
There are more than one Higgs possible to reduce cholesterol.
Sorry, more than one? Let me see what.
I mean, more than one Higgs can we?
Oh, you mean if I have, I have a gauge group, G. This is what we are doing. We are going into H with some field phi. You think, what happens if I add more fields? Well, if you go beyond the standard model, there is always more than one Higgs. Only in the standard model can be one Higgs by definition, because now I have to break that one. So there's always more than one Higgs in the physics beyond the standard model. You can ask, can I have more one and the same Higgs? For example, I use the adjoint. Can I have two adjoints? Maybe that's what you ask. Yes, that will be your homework. Then it's hard. You see, this is the privilege of a teacher. You do a trivial thing and he likes the students to do hard thing. That's sort of, a privilege of, think of great physicists. Great physicists do trivial thing. You think that they do the hard work. Of course, they are geniuses, say they do something that you will never guess. But they do the easy part. Then you sit down and do these ugly calculations, okay, that Einstein wouldn't do. Because he couldn't do them well anyway. He couldn't get his bloody equations right. I don't know if you the story, in November of 1915, he will have said, we have an archive today. So he sent it thrice, every week he's sending a revised version of his paper, every time he gets the equation wrong. He called it Hilbert-Einstein action. Hilbert had no idea about physics, as he said himself. He got the action right. Action means equations. Einstein knew everything, but he couldn't get, he needed his friend Grossman to teach him. Who cares? That's why I keep trying to tell people, don't be impressed by people who look smart. Forget that. Be impressed with people who write something that is simple, deep, and gives predictions, okay? And so, for example, an interesting question that people are studying a lot, what if there is another Higgs doublet in the standard model, another Higgs boson? The trouble is when you add more, you will see in the homework, okay? That's what I always tell you. Try to stick to minimal when you have an idea, because you tendentially lose these beautiful predictions that you have. But it's better after the homework. I shouldn't start at 12:20, right? The gauging of this. You and I can't wait to do the gauging. Because that's where the action is, right? That's the fun of the standard model, okay? And you, because you want to start learning really what this is all about. People often debate this issue. I was sort of, if you were there in my talk, I was trying to explain to people. So we can do that. Just let's get this in the last 10 minutes. I won't start the. I was trying to explain, and I find it very hard to explain. People are hung up somehow. The difference of the gauge principle and global symmetries. We shouldn't talk of gauge symmetries. We should talk of gauge invariance. You will see we only look for gauge invariance things. In a global case, we don't care just about gauge invariance. We're actually interested in the transformations in them. In a gauge case, all that can exist is a gauge invariant quantity. So I was trying to say that the global symmetry has no physical meaning, really. I don't know if you paid attention. I gave this beautiful example of Maurice Goldhaber, who is a great experimentalist that measured neutrino helicity. And he and Reines fathered the idea of large water tank detectors. They wanted to study proton decay. That will, in the early 50s, around 55, it will culminate in 98 with the discovery of neutrino oscillations in a huge tank in a Kamioke mine in Japan. Enormous, right? It has 50,000 tons of water. It's like a big swimming pool. So we can check it, maybe. Okay, we can try to check as I speak. And it's very ironic because they were looking for proton decay, which they didn't find, but they discovered neutrino oscillations anyway. So what Goldhaber and Reines wanted to do, I said for fun, they were not completely stupid. We talked some of the greatest experimentalists of the last century. They said they want to measure proton lifetime. And the funding agency says, but you guys are crazy because proton must be stable. Then why would they say that? And this is what the global symmetry is all about. You see, Maurice Goldhaber actually managed to produce this. I think this could be a nice homework in the end. If you know the amount of radiation that will kill you in a year's time, for sure, or even less time, you can put a limit on proton lifetime by the fact that you and I live on average 80 years now. He took 70. And I don't know where he got the thing, I forgot, okay, but today you can read it online, you'll find it, okay. I remember when I had to reproduce it, I found it easy. I was giving a summary talk somewhere on, review summary talk on proton and other barrier number violating processes. So you get this interesting number, which is huge. So people say, but this is amazing now. Remember, the other decays, muon decays in 10 to the minus 6 seconds. By the way, neutron takes a little more time. You remember how much to decay? Some idea?
Muons or what?
Oh, did I say muon?
No.
Neutrons. I'm sorry. Sorry.
Some minutes, I don't remember.
It's about 10 minutes, I think. Yeah. Why does neutron take more time? It's very strange. It's heavier than a muon. The heavier, the faster you decay, obviously. Massless particle cannot decay. And you told me the other day, decay is proportional to the mass, you said, of the Higgs. Without calculating, you said, it has to be.
Probably because the available phase space. For
Excellent,
the
right?
neutron.
Because proton weighs as much as neutron, basically. There is very little phase space, right? Anyway, to get the idea, right? Tau muon is 10 to the minus 6 seconds. Tau neutron is 10 minutes, but that's because MP minus Mn over MP minus Mn or vice versa is around 10 to the minus 3. Very little phase space, right?
Plus, I think plus in there. No. Denominator.
Or better. I have an absolute value smaller than the number. It's interesting. And then you get this crazy limit, right? So you say I will explain that, right? Something must happen. It's a miracle. In a normal world, proton should decay in faster than 10 to the minus 6 seconds. After all, it's heavier than the muon, 10 times. So they said, oh, but there must be some reason for this.
So that they invent a new global symmetry.
So you say, oh, well, proton carries a barrier number. Proton will decay. What could it decay into? Let's preserve charge. Charge is sacred. You and I don't want to break charge. So tell me.
Positron.
Positron plus a pion. Something else? I don't know. Maybe neutrino and pi plus.
But then lepton number will be violated.
Well,
Oh, you are considering as a whole. Okay.
I violated lepton number.
Yeah. Okay.
Oh,
I thought that you were saying that.
barrier number is much more sacred. Lepton numbers, we don't have such good limits. We'll talk about it. We'll have to talk about that because neutrino is massive, so we have to talk about massive neutrino. It seems to be related to a lepton number. It seems to be. We'll talk about it. There is no proof. So then people said, they took a long time to pronounce it. But then, the first guy has courage, I think it was Wigner, says something like, oh, there has to be a symmetry behind the baryon number. And in the beginning it's a heresy. It becomes a dogma. All heretical statements become dogmas. They either burn you or they may crucify you in the legends, I don't know the other things, and then it becomes a dogma eventually. People have to follow it then because it became a dogma. So this became a dogma. So the funding agency tells Maurice Goldhaber, we used to discuss this a lot about the failure of education. He was my colleague at Brookhaven when I worked many years there. You say, baryon number is a good symmetry, so proton cannot decay. Now you realize how stupid this is? This is tautology. It's worse than tautology because the physical fact is this. This is not. This is just your bookkeeping. You are confusing the cause and consequence. If proton is stable, baryon number is a good symmetry.
Yeah, but not the other way.
Not the other way around. However, this is still very useful because you and I know that baryon number is a good approximate symmetry. For example, from here, I know that there is a good approximate symmetry. It's called isospin. It works beautifully. But you cannot use it to say the proton and neutron must have the same mass. This is very important. Okay. So global symmetries are just our bookkeeping. Don't use them because I'm telling you, but I'm afraid you will write a paper, as even my colleagues. I have endless file with my colleague Smirnov, who will say they agree with me. He will also write a paper, as everybody else, claiming that they use a symmetry or global symmetry to make predictions. You cannot do that. You're confusing cause and consequences, and this I cannot overemphasize, okay? I say it publicly because this is what I've written. And it's very strange because there are some of us who think about that and for us it's trivial, and there is an army of other people who I don't know why this is not so clear. It seems to be clear to you, right? It's very useful that I speak of isospin. But I cannot go backwards to claim that it has to be exact. Nothing is wrong with an almost exact global symmetry. In other words, the point of symmetry is not special. So, bottom line, global symmetry is a bookkeeping. Then comes what we call the gauge symmetry, gauge invariance. There are two fundamental differences between these two. One, these are actually dynamical theories of phenomena. This is not just a question of some symmetry that you like to have. This is associated with the existence of messengers of the force. This is our way of organizing the existence of the messenger. So it has a profound meaning far beyond the actual thing of the symmetry itself, right? The dynamics is what is crucial, okay? So when I speak of gauge symmetry, and this is why we are after, and this is why this is infinitely more important than global symmetry, as interesting and beautiful they may be, and the breaking and Nambu-Goldstone boson, this is a beautiful mechanism because this is how nature seems to operate. For every interaction, if I communicate with Hassan, there is a messenger between us, whatever we do. Whether it's something carried through the air or, I use my mobile or whatever it is, there is a messenger, the force seems to be. There's another thing that I will try to teach you. Then in the case of gauge symmetries, the point of symmetry will turn out to be special. Takes time to understand, but this is what the field theory course is all about, and my lecture is called Normalizability. We'll talk about that. So this is why I don't speak too much about global symmetries. They could be explicitly broken anyway. Nothing would go wrong. And if you make a poll now with my colleagues, 90% of them will tell you they believe that proton is unstable. Anyway, this is where we stop with global symmetry. We will not address them anymore. Okay? Well, I didn't stop, sorry. Let me see if there are questions. If you have to leave, that's different. But, yeah. But I still want to see if there are questions.
Is it true that when we break a gauge symmetry, then the massless Goldstone bosons do not appear?
Well, this is what we are going to be talking about, and you can see it immediately here. Gauge symmetry means that I can change the phase arbitrarily here, right? But this is a phase, really. This depends on space-time. Therefore, how can this be physical, right? I'm allowed. In a global case, if I do that, it will go into the derivative. So boson-boson cannot disappear. But in this case, there is no derivative coupling. There is covariant derivative. That I can always adjust with changing the property of my gauge field. I have the freedom of making an arbitrary. I'm glad you asked that, because before we do anything, we have to understand in detail what happens. But we now know here, just by staring at this, that boson-bosons cannot be physical. This is the essence of the gauge symmetry. You know, when we wanted to get questions, we would organize summer schools, Alexei and I, together. And then we would organize discussions. And imagine you get, I don't know, 200 people or more, and you have the full auditorium, and there's no question. I've been in places. Actually, in summer school, there were no questions. And this guy said, well, you know, maybe we should. I said, wait, just wait. So what Alexei and I would do, we would just stay there like two dummies. And people start to feel embarrassed, you know, when you see someone who's just standing there, you don't know what to do. After 5 minutes, there is a question. You won't believe this. After 5 minutes, there will be a question. And then, the discussion would never stop. 2 hours later, they want to, you know, they get upset with us that I say, no, it's time to go swimming. This was in the summer. So I don't know whether they want to stay. Just the question. I won't do it for 5 minutes just to see if there is one last public question, okay? For the respect of the, you know, machine that is recording and the people that want to know if you guys have questions. Okay, so I just want to make sure.
Can you break the symmetry with a fermionic or magnetic field?
I cannot do this, you agree? Because I don't want to break Lorentz invariance. I could do this. This is a scalar. So I could do this. There were people who didn't like the Weinberg himself, the one of the fathers of the Standard Model and the person who introduced Higgs mechanism. And particle that should be called Higgs-Weinberg boson actually had that this would be much nicer. It goes under the name of technical theories. I will mention something when I finish with the Higgs, okay? Yes, unfortunately, this case, you don't. If it's predictive, it fails completely. If you try to sort of save it, you lose all the predictions. So, if you substitute the Higgs. But just to tell you that actually in QCD, it has been proven, this is what Nambu suspected, that something like this actually does take place. We have an example of this taking place. This is not the QC, this is not the, what is the dimension of this, help me? Cube, right? So it's not V, it's V cube. So this is some V cube. And in QCD it turns out that V is, you can guess what V is. It's lambda QCD, there is no other scale. So it's GV. So actually it does take place. Not only that it can, it does take, for sure now we know it does take place, but it has nothing to do with the Standard Model because the scale is too low. This cannot give the mass to W. But W does have a little correction from this funny condensate, okay? Obviously, in order to get this condensate that we say, you need strong interactions. To make this guy be a particle, in a sense, you have an equivalent kind of a particle, right? Strongly bind. Like the existence of a pion, for example, you know. It's not surprising that it happens in strongly coupled theory. And that's why the name for this was this Technicolor. When they immediately realized, you know, Weinberg, that of course it cannot be the QCD because the scale is bigger, then I need a color-like theory, so he called it, he or Susskind, Technicolor. Some new. And they tried SU4. You know how we do physics. If SU2 cannot work, or SU3, if SU2 doesn't work, I'll try SU3. You know, it's like Einstein's cartoon, E = mA² and so on. Okay.
So do we have good reasons to believe that there can be charged Higgs bosons?
Well, good reasons. There is something that is called Peccei-Quinn symmetry that has to do with a strong CP violation and leads to the existence of the axiom that you heard about. In that model, there are charged Higgs bosons, for sure, but they could be having masses of 10 to the 10 GeV. We don't know. That is lexopredictivity, okay? I will tell you what happens. It's like if I add a second doublet to the standard model, we will see that I'll get charged. We are running ahead. So this question, okay, it's too early to answer. Yes, we could have, if we don't know what their mass would be. So LHC is just putting limits on the masses of the charge. I don't know whether I should call them Higgs, charge scalars. Let's call them scalars because they're not really Higgses because you don't want to break charge symmetry. And that's around 100 GeV or something. I don't have a precise number.
So it's about the mass of the...
It's same mass of the Higgs boson. I think limit is not much better. There are even models in which we suggest that there is a doubly charged scalar. For example, the theory I'm advocating, there has to exist a doubly charged scalar.
Doubly charged.
Sorry, doubly charged, charge 2.
Oh, okay. Charge 2. I thought they were using plus and minus.
No, doubly charged would have actually charge 2. So it follows from the theory. So in an SU5 theory, in a grand unified theory, you suggest there are fractionally charged gauge boson and maybe fractionally charged scalars and so on. So yes, unfortunately there the scale is large. Well, we'll talk about that, okay? Maybe just one last question. I think we are okay, right? You don't have regarding what I said on. I'll close the subject of number-Goldstone bosons for the time being. Okay? Okay, we can then stop here.